This is a tutorial on acid-base equilibria. So let's talk about these ionization constants for the weak monoprotic acids and bases. If we look at the ionization for acetic acid and water, for example, we got our acetic acid plus our water forming hydronium ion and acetate ion, and we see the double-headed arrows indicating an equilibrium. We can express an equilibrium constant as we did in our equilibrium presentation. If you need some particulars about that, look at my equilibrium presentation. We can express that as a Kc equals hydronium ion times acetate ion concentrations divided by the acetic acid and the water. But water concentration is so large compared to the others that that's somewhat not necessarily to include. Water concentration is essentially that of pure water, so if the activity is 1, we can essentially move the water over there and say, well, that concentration is essentially a constant, and establish a new constant, which is going to approximately equal the hydronium times the acetate divided by the acetic acid, omitting water from the expression entirely. And that's typically what we're going to do for weak acid and weak base equilibria. So we define that weak acid, or we call that the acid ionization constant, and we're going to give that the symbol Ka. So Ka is equal to the concentration of the hydronium ion times the concentration of the acetate ion divided by the concentration of the unionized acetic acid. And for acetic acid, that constant is equal to 1.8 times 10 to the negative fifth. You can find tables of Ka's in the back of your textbook and one of the appendices, or in a table in your chapter or something like that. In a simplified form, if you omit the water and take away the hydronium, you could just leave it as H plus if you'd like, depending on your teacher's preference. So the Ka is equal to the concentration of the hydrogen ion times the acetate ion concentration divided by the unionized acetic acid concentration, and that's still equal to 1.8 times 10 to the negative fifth. Let's look at an example. So we look at these acid ionization constants for several acids. Which is the strongest? So we got acetic acid, nitrous acid, hydrofluoric, hypochlorous, and hydrocyanic acids. I give you the formula there in that second column. But what we're interested in is that third column, the Ka's. The Ka value is going to be the biggest if you have the most ionization. So the acid that is the strongest is going to be the HNO2 because it has the largest Ka value. That means there's more ionization, therefore more H plus present in the solution, because the H plus, or hydronium ion, was in the numerator of those equilibrium constant terms, which means that since the H plus or hydronium ion is in the numerator, a bigger Ka is going to be more of that at equilibrium, and therefore it's going to be a stronger acid. Let's write an equation for the ionization of the weak acid HCN, and we'll write an expression for its ionization constant. So the HCN plus H2O is going to form the cyanide ion and the hydronium ion. And then we're going to write a Ka expression for that, where Ka is equal to hydronium and cyanide ion concentrations in the numerator multiplied together divided by the HCN unionized concentration in the denominator. So let's look at an example. If we know the pH of a 0.1 molar solution of a weak monoprotic acid, which we'll just generically call HA, is found to be 2.97, we'll know the value of the ionization constant, or the Ka. So we know that a generic equilibrium would be HA plus H2O forming A minus and hydronium ion. So the pH is negative log of the hydronium ion, so the hydronium ion concentration is 10 to the negative pH power, or 10 to the negative 2.97, or 1.07 times 10 to the negative third molar. So if we use that information, we set up a table with initial change in equilibrium concentrations. We call that an ICE table. And we've got the concentration at HA, H3O plus, and A minus across the top. So initially we're starting with a 0.1 molar solution and none of the product ions. But since we know the pH of the solution and just figured out what the hydronium ion concentration was at equilibrium, we can fill in that spot, the 1.097 times 10 to the third molar. Since it's a 1-to-1 ionization, that's also the concentration of the anion. And therefore we know that that is the change going from 0 to those concentrations. Now we can figure out the HA. So that change, we're going to lose that much, the 1.07 times 10 to the negative third molar on the HA. But that's so small compared to the initial amount, we're going to end up with approximately 0.1 molar. And you find that'll be the case with a lot of these weak acids. The ionization constant is so small, you get so little ionization. When you go to subtract that from the original amount, it's not going to really show in the sig fig. So we can kind of make that approximation that the equilibrium amount is approximately equal to the initial amount. That is a bit of an approximation though. Otherwise, go back and calculate it with the quadratic equation and whatnot like we did in the equilibrium presentation. And I have one of those up on my channel. So if we write our Ka expressions, H3O plus A minus divided by HA, plug in the information from the table on the previous slide, we get 1.07 times 10 to the negative third molar times 1.07 times 10 to the negative third molar divided by 0.1 molar, and that's going to yield 1.02 times 10 to the negative fifth for a value for the Ka. So let's look at another example. Calculate the concentrations of the various substances in acetic acid solution. So we got acetic acid plus water going to hydronium ion and acetate ion. We get a 0.15 molar solution initially before any ionization occurs. So we can set up initial conditions where the initial concentration of acetic acid is 0.15, 0, and 0. But unlike the previous problem, what we see is that we don't know anything about where we end up. So what we do is we assign the change in concentration of the acetic acid as x, and so we're going to subtract that and get 0.15 minus x, and we'll assume we'll gain that amount on the product side since the stoichiometry is all 1, so plus x and plus x, and so we'll just say the concentration of the two product ions, the hydronium and the acetate ion, are x. So 0.15 minus x, x, and x. So we set up our Ka as hydronium ion times acetate ion divided by the unionized acetic acid. And so we get essentially x times x is x squared divided by 0.15 minus x is equal to the Ka for acetic acid, which is 1.8 times 10 to the negative fifth. Now again, Ka is pretty small compared to the initial concentration, so we're going to make our approximation we made before. So we're going to assume that that x is pretty close to 0 when we try to add or subtract it, and so we can simplify. We're using our approximation of x squared divided by 0.15 equals 1.8 times 10 to the negative fifth. So x squared is 1.8 times 10 to the negative fifth times 0.15 molar, or 2.7 times 10 to the negative sixth. So the hydronium and the acetate ion concentration is equal to x, which is equal to 1.6 times 10 to the negative third molar, where we're going to assume the acetic acid concentration remained approximately 0.15 molar. So the percent ionization is going to be the amount that ionized of the acetic acid divided by how much you had to begin with times 100%. So we have 1.6 times 10 to the negative third molar divided by the 0.15 molar times 100%, or 1.1% ionization. And that's what you're going to find is the ionization is usually significantly less than 10% for most weak acids in aqueous solution. If we want the pH of the solution, we just take the negative log of our hydronium ion concentration, which was 1.6 times 10 to the negative third molar, and that gives a pH of 2.8. We find we can do the same things with weak bases as we did with weak acids, except we use Kb for the weak base constant instead of Ka. So we could work essentially the same problem we just worked, except with 0.15 molar ammonia instead of 0.15 molar acetic acid, where we got ammonia plus water is going to form the ammonium ion plus hydroxide ion. We can have the same, pretty much the same table with the same reasoning, except we got ammonia, ammonium, and hydroxide across the top, initial change in equilibrium across the left-hand side. But essentially the same mathematics as we had before, except we're calculating a base, where a pH is going to be determined by hydroxide ion instead of the hydronium ion. That's the critical difference. So we're going to have a Kb equaling the product of the ammonium and hydroxide ion concentration divided by the unionized ammonia. We're going to get a very similar looking equation. X squared divided by 0.15 minus x equals 1.8 times 10 to the negative fifth. Coincidentally, the Kb for ammonia and the Ka for acetic acid are pretty much the same thing. Again, since x is small, we're going to assume the ammonia at the end is 0.15 molar, so we can say x squared divided by 0.15 molar is equal to 1.8 times 10 to the negative fifth. Solve for x the same way, and if we find out the ammonium and the hydroxide ion is equal to x, which is equal to 1.6 times 10 to the negative third, just like before. So we're going to find the percent ionization of the 0.15 molar ammonia. So the amount of ammonia that ionized divided by the initial times 100%. We plug in our numbers and see we get the exact same percent ionization as before because we started with the same concentration with the same ionization constant value, so the same. Where the difference is going to come in is when we calculate the pH of the solution. Now since that 1.6 times 10 to the negative third molar represents hydroxide ion concentration here, we can calculate the pOH is equal to the negative log of 1.6 times 10 to the negative 3 molar, which is a pOH of 2.8. To calculate the pH, we subtract that from 14 and get a pH of 11.2 for that solution. Alright, let's change gears a little bit and talk about polyprotic acids. Turns out that many weak acids do contain more than one ionizable hydrogen. These are called polyprotic acids. Examples could be acids like phosphoric acid has 3 acidic hydrogens, and more complex acids like citric acid and other acids as well. Calculation of equilibria of polyprotic acids is done in a stepwise fashion where you have to consider each of the ionizations separately and then look at the cumulative effect for each ion. One approximation is to assume that the first ionization is most significant and ignore the other two. That simplifies the calculations, but is certainly an approximation, and there's going to be some error there. Because of the time taken to do all those stepwise calculations, I'm not going to really do calculations for polyprotic, but I will point out that they're done stepwise, assuming the information from the previous ionization. But there's an ionization constant for each step. If we look at phosphoric acid, it has 3 ionization constants. The first hydrogen will come off. Ka is equal to 7.5 times 10 to the negative third. For the second ionization, it's 6.2 times 10 to the negative eighth. Ka3, 3.6 times 10 to the negative 13th. We notice that they vary where Ka1 is bigger than Ka2, which is bigger than Ka3. So the ionizations get progressively weaker, which is why you can assume the first ionization is most of the H plus or hydronium ion and go at it that way, although that is again an approximation, and you could get in trouble if that's not as true as it could be in some cases. So general relationships, Ka1 is always bigger than Ka2, so on and so forth. Carboxylic acids are organic acids that end up being weak acids and will ionize, where R is some carbon-containing group, which makes it an organic molecule, and you have a C double bonded to an oxygen and then an OH. That H attached to the oxygen is the acidic one, and that's what's going to be ionizable. Any hydrogens that are present in that R group are not ionizable and won't contribute to the acidity. Our friend acetic acid that we talked about a little bit earlier is certainly a carboxylic acid, and while you see it sometimes written with a COOH in the formula, it's indicating that carboxylic acid group. Lewis acids and bases. In a Bronsted-Lowry model, the acid's a proton donor, but if you focus on electrons, the Bronsted-Lowry acid could be considered an electron pair acceptor instead of a proton donor. So therefore, a Lewis acid we're going to call an electron pair acceptor, and a Lewis base will be electron pair donor, which that'll give us a much more generic definition for acid-base chemistry that need not necessarily even be aqueous or contain hydroxide or hydronium ion. And therefore, you don't even need protons to be an acid. Therefore, that's going to be a very generic definition, and the definition that's used, particularly going forward in a lot more advanced classes. So the Lewis acids can have an incomplete octet, like your beryllium and your boron compounds often do, and they can accept electrons into their incomplete octet. Transitional metal ions are often Lewis acids, things like iron, or even some other metals like aluminum that aren't transition metals. But you've got those vacant d orbitals, and you can accept some electrons into there, so they can act as a Lewis acid. Compounds with pi bonds can act as Lewis acids. Most notably, carbon dioxide can react with water to form an acidic solution of carbonic acid, so to say. And that's why we boil our distilled water before we do any acid-base chemistry in it, because we want to make sure that the acidity, because of carbon dioxide, is not there. Metal ions positively charge attract the non-bonding pairs on the oxygen molecules in the waters. And so we get that metal-water interaction that can be rather strong, and it creates an acidic solution, where each metal will hydrate with a different number of waters. In the case of this iron plus 3, it's 6. So the iron hexahydrate 3 plus will ionize to form an iron pentahydrate with a hydroxide group on it with a 2 plus charge and a plus 1 hydrogen ion, Ka 2 times 10 to the negative third. pH increases as the size of the ion increases, like your plus 2 calciums and zincs are not terribly acidic, and sodium is not really acidic at all, where aluminum is decently acidic. Your bases typically have a pair of electrons to donate. That's why you've got your nitrogen-containing compounds such as ammonia acting as a base. You've got hydroxide ions, and a lot of the anions of the weak acids can act as Lewis bases by donating electrons as well. This has been a brief tutorial on weak acids and weak base equilibria with a little nod to your Lewis acids and bases and polyprotic acids.